Okay, so I'm Crystal Raymond. I'm a climate adaptation specialist with the Climate Impacts Group at the University of Washington. And the purpose of this webinar today is to provide some foundational information for understanding what we expect from a changing climate in Washington State. So thank you to everybody for joining today. We know that the information may be familiar to many of you who have been working on climate change in the state for a long time. And we know that there's a lot of new staff within state agencies who are working on climate change for the first time. That group is really rapidly growing, and so this information may be new to others. And this is a chance really to provide some common foundational information for all state agency staff about climate change impacts for our state. I just wanted to mention that this webinar is organized and supported as part of the process led by Washington State Department of Ecology to update the state's climate resilience strategy. And a requirement of this strategy is that it consider climate science and the geographic variability and climate risks across our state, and that's what we'll be talking about today. We also wanted to extend this opportunity to people within state agencies beyond just those who are working on the interagency climate resilience team. And so we opened it up to all of you staff across the state agencies. And it was really exciting to see that we had about 200 people accept this webinar invitation. So there's a lot of folks here. I take that as a clear indication that people are interested in hearing more about how climate change is affecting our state. So now I think it's a good opportunity to locate the chat within Zoom and go ahead and put your name in the chat and what state agency you're with. And that way we can see everyone that's here. That also gives you an opportunity to find the chat function because we will be using that for questions today. We have just a few more people joining. Great. So we have a series of presentations for you today, and that will take up the bulk of our time. We hope to have a few minutes at the end for questions, but we also encourage you to use the chat to enter questions throughout the presentations. And we will, our team here will be answering those questions as we go. And if we get a lot of questions, more that we can answer in our time today, then we will also put together a frequently asked questions document, and we can post that with the recording and the slides of this webinar. All right, so with that, I am going to share my screen and I'll jump into the presentation and introduce the rest of our team here. Okay, great. So as I said, we're going to be talking about climate impacts in Washington State. We have several people who will be presenting today. So as I said, I'm Crystal Raymond, research scientist with the Climate Impacts Group. We have Karen Bambacco, deputy state climatologist with the Office of Washington State Climatologist, Nick Bond, Washington State climatologist, also with the Office of the Washington State Climatologist, Guillaume Mauger, research scientist with Climate Impacts Group, and Kevin Zerby, state mitigation strategist with the Emergency Management Department. Give you a quick overview of what we're going to talk about. I'll just give a brief introduction. Then we'll have a series of slides on the current science and what we can expect from climate change in Washington State. We'll talk about climate trends and projected future changes. We'll talk about really focusing on the climate drivers behind those changes and give some information on potential impacts to people, infrastructure, and natural systems. Then we'll have Kevin present on Washington State's hazard vulnerability assessment as part of the recently updated hazard mitigation plan. And then if we have a few minutes left, we'll have some time for questions. I want to start off by just highlighting a couple of key themes that we'll be touching on throughout the presentation today. So first on extreme weather. So we want to recognize that human-caused climate change is causing extreme weather events to be more frequent and more intense. Really, attribution studies are a tool we have to understand how much more. And we'll touch on a few of those for different extreme events in the presentations today. We know that we'll provide some information on climate projections and some updated climate projections, but it's important to recognize that these describe average conditions that we expect in the future. And what we experience on a day-to-day basis is really variability in individual events. And so it's important to recognize that those are additive. And in that sense, often what we feel is a combination of the climate change trend and the variability. And that can make it feel like climate change is happening faster than we expect. We will, as I said, give a few projections that come from the next generation of climate models, the CMIP6 models. And these new climate models do advance our understanding of climate change, but it's also important to recognize that the general trends in what we expect from climate change are not substantially different with each new generation of model, and that a lot of the information we have about potential impacts and changes from previous models still applies and is still relevant in most cases. And then lastly, I just want to say, a theme that we'll be talking about is essentially that as we have more warming, we expect more change and therefore more impacts. So often as we talk about the projections and the changes we expect for the future, we may talk about mid-century, we may talk about to the end of the century, and often that just means with more warming through time, we expect more change. We also need to recognize that that total amount of change toward the end of the century is not set in stone, and the actions we do take today affect both the amount of warming and the extent of the harm associated with those impacts. And so now I'm going to turn it over to Karen Bambacco, and she's going to talk about temperatures and extreme heat.
Great, thanks, Crystal. Welcome, everyone. It's good to see you all. Go ahead to the next slide, please. So first, I just want to review some of the trends that we've already seen in temperatures. This is a time series showing the January through December maximum temperatures averaged over Washington State. And annual maximum temperatures have warmed by 1.5 degrees Fahrenheit since 1895. You can see the trend line there in blue. In addition to the warming we've seen in annual temperatures, there has also been warming in all seasons. So maximum temperatures, which are typically during the day, the warmest part of the day is what records the maximum temperature. They have warmed the most in winter, and the warming is least pronounced in spring. Go ahead to the next slide, please. This is the same as the previous plot, except here we're looking at our annual minimum temperatures averaged statewide. So minimum temperatures are typically lowest at night. It's not always the case, but they're usually our nighttime temperatures. Our annual minimum temperatures have warmed by 2.5 degrees Fahrenheit since 1895. So we've seen more warming in our minimum temperatures. They're warming faster than our daytime temperatures in all seasons. And then minimum temperatures have warmed the most in summer. So that's where we've seen the most warming. Go ahead to the next slide. So the frequency of summer nighttime heat waves has also increased. So nighttime heat waves are defined using the minimum temperatures. And this increase that we're seeing in frequency, it has been occurring whether you define it as an event with 2 consecutive days over the 95th percentile, which is shown on this slide here, or whether you're using 3 consecutive days above the 95th percentile, and that same trend is also seen if you were to then look at a 99th percentile threshold in heat. So we have some really high confidence that the frequency of these consecutive nights above normal or a nighttime heat wave has increased in the historical record. This is true for both Eastern Washington and Western Washington. That's been analyzed separately. Western Washington is shown here. And each year from 1920 to 2001 is shown on the x-axis, while the day of year from June 10th to September 17th is shown on the y-axis. And you can very clearly see, so each one of those dots is the day above that 95th percentile threshold, and you can see a clustering of those events in recent decades, resulting in that significant trend. So there is not yet a significant long-term increase in the frequency of daytime heat waves. But with that said, the number of days above 90 degrees Fahrenheit, for example, has increased over the last decade in many locations. So we're seeing some increases in daytime heat, but just not on a long-term trend basis quite yet. Go ahead to the next slide. So even though we haven't seen the trend in extreme daytime heat waves, of course, we know that impactful heat waves have occurred in our state. The obvious example is the June 2021 heat wave, sometimes called the heat dome, which set 128 all-time high temperature records across Washington, including the hottest day on record in Seattle with 108 degrees Fahrenheit, and the hottest temperature ever recorded in Washington State, 120 degrees Fahrenheit. The heat dome was the deadliest weather-related disaster in Washington State history, and also impacted, in addition to public health, of course, infrastructure and our ecosystems. So many studies are coming out now about the event, and while the contribution of climate change to the magnitude of the extreme temperatures was relatively small, so in other words, it would have been a major heat wave regardless of climate change, the contribution of climate change increased the likelihood of the event. The event was 150 times more likely to occur as a result of human-caused climate change, according to one study. Go ahead to the next slide, please. So on the flip side of very hot days, the number of freezing days and very cold nights has been below normal in recent decades as well. This is consistent with the warming we've seen in winter. These two plots are from the National Climate Assessment State Summary that came out last year. And on the left-hand side there, we're seeing a reduction of days in recent decades with maximum temperatures below 32 degrees Fahrenheit in Western Washington. That's on the left side there. And then on the right side, we can see a reduction of nights with minimum temperatures below 0 degrees Fahrenheit for Eastern Washington. So we're seeing fewer of those really cold nights lately. Next slide, please. And then, of course, as I'm sure you're all familiar, rapid warming is projected in all seasons for Washington State. The plot here is showing projections for a lower emission scenario in blue and then a higher emission scenario in red through 2100. By the 2050s, we expect either a 4.4 or 5.7 degree Fahrenheit amount of warming. This is relative to an average over 1950 to 2010, depending on the scenario. So more warming with the higher emissions scenario. By the 2080s, the warming could be closer to 9 degrees Fahrenheit for the higher emissions scenario. The main point is that warming is projected throughout the century in all scenarios, although not all of those scenarios are shown here. And these are from the newer CMIP 6 projections that have been downscaled, like Crystal mentioned at the very beginning. There's also strong agreement among models that extreme heat events will become more frequent, as we are starting to see with our nighttime events already here in Washington. And go ahead to the next slide. And I'm going to pass it off to Guillaume.
All right, thanks, Karen. So I'm going to talk about a few topics, and starting with precipitation. And you all, I know, are very familiar with the landscape and the climate here, but just to reiterate, we first of all have a very strong seasonal cycle in precipitation here with wet winters. We get half of our rain roughly between November and February, and very dry summers. I wanted to show this map just to emphasize the other piece of the variation in precipitation in our region. You all know this, right? The east side is much drier than the west side, but I just wanted to emphasize just how strong that is and how different that is with elevation. So, you know, we've got the Columbia Plateau getting less than 10 inches per year in parts, and you contrast that with parts of the Upper Cascades and Olympics that are getting over 180 inches, almost a factor of 20 more rainfall. And that's something we see here in Puget Sound as well, right? Where in the lowlands of Puget Sound, For example, Seattle, we get about 35 inches. You go up the hill into the Cascades, and that can triple easily. Right, so big contrast. This is something to just, I mentioned this because it's important to keep in mind as we look at the projections in the next couple of slides, because this is a big factor that's going to drive what those impacts are, right? A 20% increase in 180 inches is very different than a 20% change in 8. Okay, next slide, please. All right, so similar to the plots you just saw from Karen for temperature, this is the equivalent for annual precipitation averaged over the state of Washington. And the contrast here is that although there is, you can calculate a trend for this time series, it's very small and it's not statistically significant. And maybe more importantly, it's much smaller than that year-to-year variability you're seeing here. So, you know, it'd be hard to experience the year 2015 and think of, well, 2015 is a bad example, actually. Experience one of the years in the recent decade and think about how that feels different than some of the years earlier in this record, right? So really not much to speak of in terms of winter precipitation change or annual precipitation change. If you look at trends in other, this holds true for basically anything you look at with precipitation, with some minor exceptions. You can see trends in some cases, but they're not generally consistent with each other by location or depending on how you look at them. So if you look at winter or summer, extreme precipitation, we don't have a lot of trends looking backwards. Those are more in the projection. So let's move on to the projections on the next slide, please. Okay, so this is again showing annual precipitation, but this time from models. The gray there is what the models are saying, are showing for historical annual precipitation trends, and then those colored lines are same as that plot you were seeing from Karen earlier. 2 different greenhouse gas scenarios showing how annual precipitation may evolve going over the next century. And what you see similar to that, the observations, it's really not much of a trend. It's a very slight increase, and it's much smaller than that year-to-year variability. And then here, the one thing in addition to the observations is you have that wide range of variability relative to the trend, but you also have a wide range among the model projections. So what we find looking at annual precipitation trends is that there's a wide range among models, including some models that show decreases in annual precipitation, even though on average, what you're seeing is the average model line there. There's an increase, there's quite a wide range around that, and there's some disagreement on even the direction of the change. So that's all annual precipitation. What I've said so far for annual, though, applies just as much to winter precipitation. Summer precipitation is different in that the models tend to show a decrease, and it's also different in that the percent changes are larger than what we're seeing for annual and winter precipitation. There's still some disagreement among models, even for summer, on the direction of the change. But in general, there's more consistency among models that there's a decrease to be expected in summer. And then finally, the big contrast with all of these is extreme precipitation. And that's where there's a lot more model agreement that those extreme precipitation events are going to become more intense in the future. If you could go to the next slide, please. And that's what I wanted to talk about here. So this is actually showing some relatively new results from some regional climate modeling or dynamical downscaling for our region, which past research suggests does better at capturing changes in heavy rain events or extreme precipitation. So what you're seeing in the top left is similar to that first map I showed. It's showing the historical distribution of the 25-year event in this case. So the 25-year precipitation intensity. And you see that same thing from that first map where there's those high elevations and the Cascades and Olympics, especially the southwest facing slopes, have the biggest intensities, and there's that wide range across the state, right? Columbia Plateau is, relatively speaking, much lower, even for the 25-year event. Okay, so the other maps are showing those projections going forward for Ecology's regions for the 2030s in the top right, 2050s in the bottom left, and 2080s in the bottom right. And if you just focus in on the bottom right map, that's where we see the biggest changes, looking out farthest in the future. And I should mention this is for a high greenhouse gas scenario. So this is the high end of what we might expect. What you're seeing there are the average projections among models. And then those ranges in parentheses, that's not actually the range among models. That's just that's the range actually within each region. So you can see there's some range in that average projection, in some cases relatively large. But I think the big picture take home here is that on average, what the models are saying for all these regions is relatively similar in terms of the percent increase, right? So whereas that top left plot really clarifies that we get different amounts of rains in different parts of the state, we know that, right? But in terms of the percent increase, it's all in the ballpark of about a 20% increase by the end of the century on average. Okay, next slide, please. All right, so transitioning from precipitation to sea level, you can go to the next slide. So what have we seen in the past? So this is the statistic for the Seattle tide gauge, which has been around the longest in Washington State. If you look at those trends, so this was from a few years ago. The trend was looked at through 2008, and there was about 8.6-inch rise in that time. We've had 15 years elapsed since then. And so now, if you look at the trend through today, it's closer to 9 inches or even a little bit more that we've seen since 1900. So that's the first thing to know, clear trend looking backwards. The other thing to know is that about half of that trend, we estimate, is due to climate change. And the other half is more related to the geology of our region, and in particular, the tectonics. So this is not a climate change effect, of course, but worth knowing about. In Seattle, we happen to have subsiding land related to the region's tectonics. So the land is falling, and that means the sea level relative to the land is going up. And that accounts for about half of that rise. And we know that in part because we can look at other tide gauges where there isn't that rise, or where that same subsidence, or there's even some rise in the land elevation. And if you account for those estimates of how the tectonics are affecting things, you average out to about half of what we've seen in that century. So 4 to 5 inches rise due to climate change in that time. All right, next one, please. Okay, and so again, this is looking forward. These again are the median projections, and that's the maps showing how those differ around the coastline of the state. And there's a range in those median projections from about 1.5 to 2.5 feet by 2100, with acceleration to that point between now and then. And again, this is for the high greenhouse gas scenario. So if you lower greenhouse gas scenario, would be slightly lower. And most of that range between 1.5 and 2.5 is really accounted for those geologic factors that I was mentioning earlier, right? So some places are subsiding, they're going to see more of a rise, and some places are uplifting and they're going to see less of a rise. But in all cases, we expect a rise in that ballpark. This is from the projections we put out in 2018. There is a newer national study by NOAA which suggests these numbers could be a little bit higher, up to 6 inches higher, but roughly in the same ballpark. The other thing to know is that these are the median projections. So there's quite a bit of a range around these based on the science of sea level rise, and they can range from by 2100 to a rise of less than 1 foot to rises that are well above 5 feet, and in some cases quite a bit beyond that. So that's the range of estimates. That high end of the range is way up there, in part because of uncertainties around how Greenland and our Antarctic ice melt will proceed, specifically in terms of how much those would accelerate. So that's the uncertain part in those. The last point to make is that the current science at this point does not indicate that there's going to be any change in storm surge or waves. So for instance, studies looking into the high wind events, there isn't evidence that those are going to become more intense, and the other factors leading to waves, same thing. So we don't expect those to change. What we do expect is that the base sea level on which those happen is going to rise, right? And so it's going to, even if you have the same amount of surge or the same height for waves, they're going to reach farther inland. They're going to cause more flooding. So we can go to the next slide, please. And that's what this infographic really highlights, right? And so you see these lines for current sea level and future sea level, current high tide, future high tide, and storm surge. And so even if you have the same, like let's say you have a foot or 2 feet of storm surge, if you've also had a foot or 2 feet of sea level rise underneath that, you're going to have a higher reach for that storm surge, even if it itself has not changed. Okay, I think you can go to the next slide. And I wanted to illustrate that. This is actually from a nice analysis done by the city of Olympia about 15 years ago. And they basically took that same evidence base and said, well, we'd like to know how often we're going to have to contend with the 100-year flood events. And that map on the right is showing the depth of inundation during their 100-year coastal flood. And so they just simply asked, we know how our curve relates a 100-year event to the elevation of the ocean during those events, right? And our 10-year event, how high is the water during those events? So let's just bump that curve up by 0.5 foot and ask how much more often that means we're going to see today's 100-year flood of elevations. And that takes you from a 100-year event to an 18-year event. So about a 5-fold increase in frequency. And if you then go another half foot up to a foot of sea level rise, then today's 100-year event becomes a 2-year event. So happen every other year as opposed to almost never. So a huge change for just a 1 foot of sea level rise, which is something we're highly confident is going to happen in the next couple of decades. So really dramatic shifts in the frequency of these events and how often folks have to contend with them. Okay, next slide, please. Okay, so I want to talk now about, I'm going to transition from sea level to talking about the hydrology of our region, and specifically the snowpack and streamflow changes we expect. If you could go to the next slide. And I want to start by talking about snowpack. And I want to talk about snowpack because it's kind of the canary in the coal mine for our region. Snowpack, snow melts at the freezing point, as everyone knows, which means that, we have, with a small amount of warning, we have the potential to lose a lot of snowpack as you raise the snow line. And so, for instance, there's a study, there's a typo in there, a UW-centric typo. That should say US instead of UW there on the text, sorry. A recent study came out a few years ago that looked at the trends in snowpack across all of the Western US and found that on average, we've already seen a 15 to 30% decline in spring snowpack. This is across all of the Western US. If you add up the volume of water that corresponds to, it's equivalent basically to the volume of Lake Mead. So it's a massive amount of water less that is no longer stored in snowpack and instead running off in winter into our streams. Okay, so let's go to the next slide. Okay, so now I want to show you a little bit about what that looks like, and I want to explain a few things first. So what I'm showing you here is April 1st snow water equivalent. So snow water equivalent is just the metric we use to measure snow. It's the amount of water in the snowpack. So we can think about it in those same terms as you'd think about, like, for instance, rain, a 1-inch rainstorm. And then April 1st, the reason we look at April 1st is that just happens to be, for our region, about when we reach peak snowpack, right? So through winter, you're accumulating, and then in spring and summer, you're melting, and right in between in most places is April 1st. So here you're seeing what we had in the past. This is our model estimate of the 1980s, and it's what you'd expect, right? You see more snow in our mountains, Olympics, Cascades, and then a few in Eastern Washington. And then I'm going to march through what that looks like today and into the future. So the next plot is the model estimate of how that's changed roughly in today's conditions. And so what you're seeing going from the dark reds is a nearly 100% decrease in the April 1st snowpack, all the way up to those light yellow colors where nearly no change has occurred. And you see basically what that shows is basically the snow line marching uphill, right? So biggest losses at those lower elevations and no loss to speak of at the high elevations that aren't really affected, at least by April 1st, by any warming. So that's today. We can go to the next slide for middle of the century, further loss, and then the next slide for end of the century, and a dramatic loss in April 1st snowpack, right? So just to be clear, we can still have snow events in these areas. We're talking about April 1st here, but this is still a dramatic change, right? And it's going to really transform the hydrology of a lot of places that are influenced by this snowpack upstream. Okay, next plot. And just to illustrate that, I want to walk through what that looks like for one example watershed. In this case, I'm showing the Yakima River. This is our model estimates of flows on the Yakima River, and we've actually deliberately left out the influence of dams here to just look at what the natural effects would be on flow. So what you're seeing here is a typical way that we look at stream flow in our region. It's monthly average flow for the water year. So it's going from October to September. October is on the left there, September on the right. And then you're seeing those average flows on the Yakima in this, in this world where there's no dams. And so what you see is what we've experienced over the last week, right? We had a lot of rain in the last week. You see flows come up, right, in November and December there. And then you see them drop back down in January and February. That's because the temperatures have gotten colder. Now when those precipitation events come through, that water is getting more stored as snow. So you're getting less water in the river. That continues to store as snow through the spring and then melt in that May and June peak. That's the spring freshet. And then tapers off through the summer as the snow recedes and disappears. So that's what we have. That's our 1980s conditions, right? And so thanks for moving forward. Yeah, so what do we expect with more warming? Okay, so winter, we're going to have more rain, less snow. So we expect that winter bump to go up. Because we have less snow and because it's warmer, we expect that snow melt to happen earlier, so an earlier peak in snowmelt. And then again, because we have less snow, we expect less snowmelt contributing to flows in spring and summer. So that's what we expect. If we go to the next slide, this is showing, again, today's conditions compared to the conditions of the past. And then the next slide is mid-century. And then the next slide, end of the century. And by the end of the century, that red line, we've transitioned from what was historically more of a snow-dominated system, where that snowmelt peak is really our big event of the year, to more of a rain-dominant system where most of our flow is coming down the river in the winter. And we've got a lot less coming down in summer. So this is a really, oops, could you go back, please? So this is a really dramatic change in the hydrology region. Yakima is a particularly sensitive basin, but it's not unique, right? And the effects of this are going to be different depending on what watershed you're looking at. And in particular, how much of that watershed is pulling from areas that are near or not far above the snow line, right? Because those are the places where you're going to lose snowpack. And I want to mention two quick things that we'll dive into in a little bit more depth in the coming slides. And the first is that piece that I was saying about winter flows going up, right? That red line so much higher than the black line there. So we're seeing monthly average flows here, right? And in reality, of course, stream flows don't follow that monthly average curve. They spike up and down when storm events come in, right? So the same consequence is going to happen for those spikes during flood events. So what we expect is that we're going to have bigger floods when we have less snow. And I'll come back to that in a second. The next thing I want to mention is if you're looking at the August-September piece, there's a dramatic decrease because you've got less snowmelt and runoff then. And there we can go to the next slide and look at what those consequences are. Okay, so this is from a study about 10 years ago that looked at about 300 streamflow sites across the Pacific Northwest. So each dot there is a different streamflow site. And the color of the dot indicates the change in low flows by the end of the century for that location. This is for a moderate greenhouse gas scenario. It's a little hard to see, but basically all of those dots indicate a decrease in flows. So basically universal decreases in low flows, almost without exception. And then the big brown dots, those most prominent ones that you can see, that's more than a 50% decrease in low flows by the end of the century. So really dramatic shifts in the amount of water coming down the rivers, the amount of water for habitat and for other purposes. The primary driver of those change is that loss in snowpack we were just talking about, but I want to be clear, there's other potential climate change impacts on that. I consider them secondary, both because the effect is probably smaller and because there's more uncertainty about those changes. But the tendency is the same. Higher temperatures and are going to lead to greater evaporative demand in many of our watersheds, and we're seeing that effect in this as well. And then that projection for long-term decreases in summer precipitation, that's another potential influence. Okay, we can go ahead. Okay, so transitioning the flooding. We can go to the next slide. And here I want to really revisit the three topics I've talked about so far. Declining snowpack is a major effect, as I mentioned. I think it's worth just talking about, because it can be unintuitive sometimes, why exactly declining snowpack is leading to bigger floods. It's like I said, of course, more rain, less snow. Another way of thinking about that, though, is that as the snow line goes up, you've basically got a larger watershed, right? Because more of that area is receiving rainfall, and that rainfall can go straight into the river, as opposed to snowpack, which stays on the landscape until it melts. So declining snowpack is a major factor. Another factor I mentioned earlier, heavier rain events, those are becoming more intense. That was that 20% number by the end of the century I mentioned earlier. And then sea level rise, of course, in the estuaries and the coastal areas can compound that. And so these three combine, right? So there's places where you can have all three of those factors adding together to make all of them combine and push in the same direction, right? To make flooding worse. Other thing I wanted to mention, these are I mentioned these and I emphasize them because they're the direct impacts of climate change on flooding. There are two indirect impacts that I think are worth mentioning, and that's sediment and landslides. Those more sediment coming down rivers can mean it gets deposited in channels and leaves less capacity for floodwaters, meaning it's easier to flow out of the banks. And wildfires, and those can have a variety of effects, such as making our watersheds flashier because they're retaining less water on the slopes and sending more into the river, and also affecting the amount of debris that ends up in the rivers, and that affects flood damages as well. I did not highlight those on the slide, and I mentioned those as a secondary effects for two reasons. One, they're indirect, right? So it's a little harder to tie them to climate change. And two, they're not just affected by climate change, right? They can be affected by lots of other factors, including other human influences that are not related to climate change. Okay, and then I want to just show in the next slides 2 illustrations of the kinds of impacts that we expect from flooding. If you could go to the next slide, please. And so the first I wanted to highlight is these devastating floods that happened in the Nooksack River in November of 2021. Many of you probably remember there was a lot in the news about this. This was the flood that famously crossed the border into Canada and caused enormous damage there as well. And what we're looking at here is the lower, the US side of the border, and this is the lower Nooksack River floodplain. You can see it's flooded and going out into Bellingham Bay in the distance. And just for reference, it would be behind in the other direction that the flow jumped the banks and went into Canada. So this flood, we have some collaborators in British Columbia who did a study actually to understand how much influence climate change had on that flood. And if you can go to the next slide, this is the study that's cited in the bottom here. And they found with their modeling about a 2 to 4-fold increase in the likelihood of this flood event due to climate change, i.e. we're already seeing the effects on the likelihood of events, right? So this, just like the heat wave that Karen mentioned, this is another one that's already happening and that there's evidence has gotten worse because of climate change. Okay, that's the first example. The second example was, go ahead, you can go to the next slide, is a start of an odd starting point. You wonder why I'm showing you the Walmart. This happens to be the Walmart parking lot adjacent to the Skagit River in Mount Vernon, Washington. There's some consultants who took this picture and then modeled where today's 100-year flood elevation would be. And that's the next slide, if you could show that. So this shows the elevation of water in that location for today's 100-year flood event based on the latest modeling from FEMA from a few years back now. So why am I showing this? We're talking about climate change. So the 2 things. One, we know in the Skagit that this is actually, this is just contextual actually to mention. The levees don't hold back the 100-year flood. So this is behind a levee, but this is after overtopping. And second, there's a study from a few years ago, and if you can go to the next slide, that looked at how much more often we would be seeing flood at this elevation. So what they found is that today's 100-year flood, this water elevation, would be happening on average about every 22 years by mid-century. So in just a couple of decades, it's happening 5 times as often as it would be happening in the past. So again, just like with sea level in Olympia, you know, the projected changes we're seeing are going to really accelerate the pace of changes in the impacts. And I think it's worth noting that often for these really big floods, the ones that are particularly devastating, we are often talking to a 20 to 30-year recovery time. So this could really have implications for, you know, resilience and the ability to bounce back after events of this kind. Okay, I think next slide, please. Okay, and I'm handing it off to Karen to tell you a little bit more about.
Guillaume, we have 5 minutes and there are a couple of questions in the chat that I've answered. So maybe I'll just pause here and have you answer one of them because I think it's a good clarifying question. So is the percentage change in extreme precipitation a change in volume of precipitation or number of events?
That's a great one. So it's a change in the intensity. So it is so like I showed you earlier, we don't expect on an annual basis precipitation to change significantly, but we do expect those high intensity events to become more intense, right? So in that particular case, I was showing you the projections for the daily precipitation totals or 24-hour precipitation totals and how those were increasing. We do see the same thing if we look at, for instance, the 1-hour precipitation totals. And those projections are slightly different, but similar in magnitude. And maybe this is just a good occasion to emphasize that what the research shows is that we're really talking about the same storms, more or less, but that they're able to wring out more water when they do rain, right? So we don't see things like the number of storm events hitting our coast changing or the low pressure getting lower or the winds becoming more intense. We simply see that warmer air holds more water, and that means that more can rain out when those big events happen.
Great. And maybe I'll ask one more. I answered this a bit in the chat, but just in case others aren't seeing it. So the question is extreme precipitation something that we should be fearful of? You've talked a little bit about its contribution to flooding. And then also when we're having such a problem with wildfires, more precipitation be good news? So can you say just a little bit about the pros and cons and seasonality of the precipitation?
Yeah. So, I mean, I think that I don't know how to answer the question about should we be fearful of it. I think that we have lots of risks that we deal with, and we deal with them well. And that's why part of why we do our work, right, is we want to help manage those like we do with many risks. That's what I would say there. And I think then there's a secondary question and maybe a longer conversation about the relative risk posed by the increase in precipitation versus other changes we're talking about. And then as to the wildfire question, yes. So as Crystal alluded to, our heavy precipitation events primarily happen in winter, so not during fire season. And in fact, there is that tendency among the models for drier summers, and i.e. less precipitation in summer. And so that would actually exacerbate the potential increases in wildfire, which you'll be hearing about more later.
Great. All right. And continue to enter your questions in the chat if you have them, and we'll answer them there, or if we have time, we'll answer at the end. All right, Karen, I'll turn it over to you.
Great. Thanks so much. Thanks, Guillaume. Go ahead to the next slide. So I'm going to talk about drought a little bit. And as you may be aware, there are many different ways to get drought in Washington. I think the first one that comes to people's mind when you mention drought is the dry winter type drought. So this is where you just exactly what it sounds like, have less precipitation than usual over the winter season, which, as Guillaume showed, is our climatologically wettest part of the year. This is also sometimes referred to as a dry snow drought. And this is because, of course, when you have less precipitation, you're not going to build the snowpack as you usually would. So examples of dry winters that led to snowpack drought in Washington, 1977 was a big one, and then also 2001, where it really was a lack of winter precipitation. But there's also drought that can be driven by a warmer winter. So this is warm, so it's causing precipitation to fall more as rain instead of snow, and thus impacting our snowpack. This is sometimes called a warm snow drought. And so we had that in Washington State to some extent in 2005, but worse in 2015. So that was our big 2015 drought, where we had near normal precipitation throughout the winter in Washington. But because our temperatures were so warm, we did not get the snowpack that we were expecting to get. There's also more recently in 2021, we had a dry spring type drought where we had really large precipitation deficits in spring. And then also in the summer of 2003, more of a kind of a typical drought where you're having a drier than usual time of year. So we saw that too. Go ahead to the next slide, please. So in a changing climate, there are different drivers that are expected to align to cause more frequent and intense drought. More specifically, that warm winter, that warm snow drought that we saw in 2015 is the type of drought we expect to see more of in the future. So due to increasing air temperatures, causing less precipitation to fall as snow, less snowpack, and then on top of that, the expected decreases in summer rain would make that sort of warm snow drought worse once you're getting into our dry season. So of course, summer is dry as is, but that occasional summer rain can be really important in dry years, particularly for ag and for reducing wildfire risk. So that could be an additional factor in making drought more worrying for our future. Next slide, please. So 2015 was a really good example of this changing future. I would say there's only really one key difference. So we saw the warm temperatures, the warm winter temperatures, really the whole year was warm. It was the warmest year on record for Washington. But we also had a drier than usual April through September. So it was the 5th driest April through September in Washington. So while we expect to see drier summers in the future, we aren't necessarily expecting drier springs. But I think this is really an important reminder that we're still going to see that variability in conditions that could either compound and make a situation worse, or maybe even better than expected, with the expected changes due to climate change and then variability on top of that. And then, of course, it resulted in our lowest snowpack on record for Washington. We were at about 30% of normal in 2015. Go ahead to the next slide, please. So finally, this is a somewhat complicated plot, but I'll walk you through it to show that the winter temperatures of 2015 will become more normal by the 2050s in the Pacific Northwest. So this is for the whole Pacific Northwest, so it includes Washington, Oregon, and Idaho. And on the y-axis, we have the relative change in temperature from October through February. And then on the x-axis is October to February precipitation. Each of the smaller circles is a historical year from 1896 to 2015. And then they're color-coded by decade. So you can see kind of the wide range of conditions around the center point on this plot here. But the larger and heavier circles, squares, diamonds, etc., all those shapes are all climate model outputs for 2040 to 2069 under a lower emissions scenario. And they're clustering to the right of this precipitation line and above the temperature line. So they're showing a slightly warmer and slightly wetter future for the Pacific Northwest at that point. But really the point I want to make here is you can see 2015 on the top there and 1934 called out as years that were more aligned with this model average for the future. So those types of years we expect to become much more common by the 2050s, illustrating that warm snow drought is, I think, the biggest worry as we move into the future. Go ahead to the next slide, please. And I will pass it to Crystal.
Great, thank you, Karen. So now I'm going to talk about a couple impacts related to those drivers, and I'll start by talking about stream temperature. So another impact that we expect is that August average stream temperature, which is shown in these maps, is projected to increase in many locations across the state. And this is because of a combination of factors. So it's both the warmer air temperatures that Karen talked about in the beginning, as well as lower stream flow in the summertime that Guillaume talked about, and also potentially earlier snow melt. And all those factors can come together and result in warmer stream temperatures. And this has implications for the habitat quality for aquatic habitat and cold water fish, such as salmon. And these maps show color coding associated with different temperature thresholds in the stream that are relevant and have different impacts on salmon. And so the important thing to see, so the historical map is up in the top, and then we have the 2040s, so mid-century, 2080s, end of the century, is that we see more area of the streams reaching those very high and potentially lethal thresholds for salmon. And we also see that there's some geographic variation in where that is. So there's a couple areas within the state that stand out as changing the most, the southwestern corner, the Puget Sound region, and the southeastern corner of the state, all standing out as regions showing the most change and warming of summertime stream temperatures. Another impact that I want to talk about is wildfire. So we started talking about this a little bit, and I can go into a little more detail on this. So several recent studies have shown that human-caused climate change has increased wildfire activity in a number of ways. So it's increased the area burned, the frequency of very large wildfires, and it's lengthened the fire season throughout the Western US. And this photo shows orange and red areas are all the wildfire areas that have burned between 1984 and 2022 across the West. And so we see a large amount of area has burned. And as I mentioned, those attribution studies, so there have been some attribution studies related to wildfire that have indicated that climate change has caused more than half of the increase in forest fuel aridity, or the dryness of the fuels and vegetation in the forest, since 1979. And climate change has also approximately doubled the cumulative area burned in forest fires since 1984. So it's important to note that climate change is one of the drivers of this increase that we see. in area burned and fire frequency, but there's other factors too. And fire suppression and forest management also play a role. And that's important to note because that has implications for the solutions, because the causes are multifaceted, so are the solutions. Similar to the slide that Karen showed, I want to talk about the combining forces that contribute to how climate change affects wildfire activity. So we know that these increases in air temperature combined with decreasing precipitation in the summertime contribute to the drier fuels or drier vegetation throughout the fire season, and that increases the potential for wildfires. We also know that potentially at higher elevations, earlier snowmelt can result in those higher elevation forests and areas being covered with snow for less time, and therefore that gives an opportunity for the vegetation and fuels to dry out and increase the potential for wildfire at high elevations. This is also mentioned a little bit in the chat, but I'll mention another factor. Can be heavier precipitation in the wintertime can actually lead to greater wildfire risk in the grassland environments, because that heavier precipitation in the winter actually causes more grass fuels, which then contribute to more wildfire potential in the non-forest environments in our state. I want to talk a little bit about the geographic difference in our understanding between the connection with climate change and wildfire in Washington. So even with this change that I've talked about, we still expect Eastern Washington to continue to have the greater wildfire risk moving forward. And that's because that's the area that already is more fire prone and has more wildfire risk. And that's despite increasing potential for wildfire in Western Washington. So most of our area burns in Eastern Washington or Central Washington. We expect that to continue to be the case even with climate change. But there is also an effect in Western Washington. And it's important to note that very large wildfires have occurred in Western Washington. This is a photo of the 1902 Yakult burn in southwestern Washington, about 240,000 acres. We also know that the Labor Day fires of 2020 in southwestern Washington or southwestern Oregon are a great example of that as well, and the potential for these very large wildfires. And so climate change plays a role, right? It contributes to that fuel aridity. So climate change can set the stage. But we also know, based on these recent events, that wind is a really critical factor and a big driver of the very large wildfires in Western Washington. And currently, based on climate models, there's no evidence for changes in the winds associated with wildfires in Western Washington. I also just want to say a little bit about the air quality. So over the past decade, throughout the US, the number of people experiencing wildfire smoke levels that are deemed unhealthy has increased dramatically. And particularly what's unhealthy about the wildfires smoke and the poor air quality associated with that is exposure to PM 2.5, which is the large particulate matter in wildfire smoke. And so this increase comes just from, as I've shown in the maps, of the increase in area burned throughout the Western United States and also into Canada. And we know that certain populations are more sensitive and more likely to be affected by that exposure to PM 2.5. Now, it's important to keep in mind, we don't need to have those wildfires in Washington specifically in order to get this greater exposure to wildfire smoke and unhealthy air quality. So as we've experienced in this region, we can get poor air quality coming from wildfires in Canada or other parts of the Western US. And it just depends on the weather patterns and the wind patterns at the time as to whether or not that smoke comes into our region. Okay, and now next, I'm going to turn it over to Nick Bond, and he's going to talk a little bit about evaporation and ocean conditions.
Yeah, thank you. Just a few more tidbits before turning it over to Kevin. And if you could go to the next slide. What I have plotted here are actual observations, 3 spots in the Columbia Basin of Eastern Washington. And the parameter here is the summer mean potential evapotranspiration. There's a lot of syllables there, but the idea is this is how much water on average per day would be drawn out of a irrigated field of alfalfa, and relates to how much sunlight there is, how windy it is, the relative humidity, and so forth. And the idea there is for these 3 spots, particularly Odessa and Lind, that don't have a lot of irrigation near them, that over a record going back to the late 80s, there's an upward increase in this parameter, essentially the water demand in that region, less so in LaGros near the confluence of the Snake and Columbia rivers, because it's a more irrigated area. Our climate models, spared you don't have a plot for that, but they're indicating as a group that this will continue to, this parameter continue to rise. We're less confident of that because we're not sure if the models can get how sunny it's going to be exactly right and so forth. But there's no indication that this trend will turn around and reverse anyway. So now let's go to the ocean. And in particular, the next slide, I'd like to focus your attention on this time series of sea surface temperatures relative to a baseline level for a box about 1,000 kilometers on a side off the coast of the Pacific Northwest. We've got reasonable estimates of the sea surface temperatures back over a century. You can see that, lots of year-to-year, multi-year variability. And then toward the end of the record, whoa, look at that big spike there. That was the blob, just temperatures that we hadn't seen before, and kind of alarmingly in just the last few years, also an increase. And just in the last decade, the idea of these marine heat waves has become, greater interest and attention. And just as an aside, in the climate system as a whole, the oceans have taken up more than 90% of the extra heat in that system when you take into account the oceans, the cryosphere, the ice packs, the atmosphere, and land surfaces. So the ocean is definitely warming. We go to the next slide, kind of a perspective on that is here, what those changes in temperature mean there, particularly for marine ecosystems. There's 2 sets of bell curves there, one for the atmosphere at the left and for the ocean at the right. And because the background variability in the atmosphere is greater, even if there's a greater shift in temperatures, the number of heat waves relative to some threshold that increase won't be as much as in the ocean, which has much less inherent variability. And so there's what we're expecting and already seen is a lot more marine heat waves, instances in which the oceans reach these thresholds of the 95th, 99th percentile, whatever. All right, next slide. Let's look at temperatures being projected for our waters. Here on the left, looking toward the end of the century compared to the historical times, are some model projections. The redder the color is the greater the change in temperature. And you can see right along the coast of the open Pacific, greater warming than the inland waters of the Salish Sea. That's partly because the source waters for the Salish Sea are at depth and not warming as fast as the surface waters. And so you might think, well, that's pretty good news for the critters in the sound and so forth. But if you look at the right there, in terms of, we're also expecting that the shallow estuaries of the Sound to warm more than the kind of open waters of the Sound. And so those can be critical habitats for juvenile salmon and other species that, are very important to us. Okay, next slide. It's not changing. Oh, yeah. Okay, there we go. And, obviously, it's not just the temperature, heat contents we care about, but the chemistry of the ocean. And you may have heard about this concept of ocean acidification. What I'd like to just show you with this next slide is a plot of how that's changing in various waters of Washington State. And here, yeah, it looks like somebody ate a bunch of Skittles and, got sick to their stomach or something. But, bear with me here. This is for different waters in Washington State. And on the left is the observed trends over about the last 30 years or so in pH, and with a lowering pH acidification, and at the right with dissolved oxygen. Those black dots show that where they're both declining. The red dots were places where there's the pH is going down systematically, but dissolved oxygen concentration is not changing statistically. Run the purple dots for what it's worth, where there's no systematic changes, and it's a very complicated oceanography. These differences are due to the various, the differences in the source waters and the biological mechanisms and so forth. And so the reason I put this up is one size we are seeing ocean acidification in general, but that's not yet being expressed as strongly in some places as others. And I think that'll do it for me. And
Great.
Yeah.
Great. Thank you, Nick, and thank you to Karen and Guillaume and all our presenters. We've put a lot of information out there. That was a quick run through of climate changes, climate drivers, and impacts. As we said in the beginning, this is recorded, and we'll make that recording available. We'll also make the slides available. Each of our slides have a source for the information. So we'll make a list of those sources available as well. And if you have any additional questions, you can enter those into the chat. And I think we will have time at the end for a few questions, and we'll compile those and make a list of frequently asked questions. So we presented a lot of information at you. We want to take a moment now to switch gears, and I'm going to introduce Kevin Zervy, who the state mitigation strategist with Emergency Management Department, and he's going to be talking about the state's hazard vulnerability assessment. And I think this provides some really important historical context in understanding where our natural hazard disasters are, and a more detailed look at the spatial variation in those climate-related natural hazards across the state. So Kevin, do you want to go ahead and share your screen?
Yeah, sure thing. Okay. Find my mouse. And how does that look? Does it look okay?
That's great.
All right. So yeah, thank you, Crystal. As she mentioned, I am the state mitigation strategist at the Washington Emergency Management Division. For those of you I don't know, what that essentially means is I'm responsible for understanding how Washington's risk and vulnerability to various natural hazards changes over time, and understanding how natural hazards are placing our state's critical assets and populations at risk, and making sure that that is all synthesized into our state's enhanced hazard mitigation plan, which I will mention in the next slide. So all of the information I'm going to talk about today is going to come from our very recently updated 2023 Washington State Enhanced Hazard Mitigation Plan. The basic gist and idea of this plan is to provide an overview of Washington's hazardscape So that includes climate-related natural hazards, as we've been talking about today, as well as our geological natural hazards. So within our plan is also profiles related to things like tsunamis and earthquakes and volcanoes, although I won't mention those today. The foundation of this plan is the Hazard Inventory and Vulnerability Assessment, or HIVA for short. The HIVA is comprised of a number, over a dozen different profiles for each of our natural hazards that we experience in the state, and provides basically an overview of what the risk looks like, how it might be changing over time. And as I mentioned, this is basically a brand new plan. It was just approved by FEMA a little over a month ago, and we have a 5-year approval period. So this will be the state's official hazard mitigation plan until September 30th, 2028. So for the next remaining portion of my talk, I'm going to be going over some of the summaries and results that we got from our hazard analysis, and talking specifically about some of the climate-related natural hazards in our HIVA, by going over kind of what we found and summarizing what's in our hazard profiles within the plan. But before I do that, I did want to just kind of set some context for you, to give you a better idea of how we approach this kind of work and our approach to hazard analysis. And just to let you know that our hazard profiles really are designed to accomplish 3 main things that are set by federal statute. One is that they have to provide an overview or an outline of the location and extent of previous hazard occurrences. We have to identify the probability of future occurrences. And the way that we do that is, in Washington anyway, is by looking at declared disasters specifically. So that can include state declarations or presidential disaster declarations. And that's important to note because declared disasters especially, are really a function of not just the natural system, but the way that natural system interacts with our built environment, with critical infrastructure, with population. In order for us to get a disaster declaration, there has to be some consequence of the natural event. It can't just be a wildfire. It has to be a wildfire that impacts the built environment in some way, or we won't get a disaster declaration. So hopefully that makes sense. And then the third objective of our hazard profiles has to be a summary of the expected changes that the changes that we expect to see in location of hazard events, their extents, which is defined by their magnitude or their severity, and not just geographic extent, as well as the probability of future occurrences due to changing future conditions. And those future conditions have to include climate change. We do have to consider climate change in our state plan now, as well as the other factors that contribute to disaster declarations, like I mentioned. So FEMA is interested in not just how climate might be changing, but also what do we expect to see in terms of continued population growth or urbanization, or the changes in where critical assets are located in the distribution of our population over time, and how might that influence our vulnerability and risk going forward. And so the result of all of that work is a determination of which region is most at risk to each of the natural hazards that we profile in our HIVA, and an overview of that region's vulnerabilities. And so I'll talk a little bit about that based on hazard for the remaining slides. First up is drought. So unsurprisingly, given what has already been discussed today, drought is a statewide natural hazard, but most severe risk is located east of the Cascades. And according to our assessment of where state-owned assets and populations currently are, it appears that central Washington would be the most at-risk region for drought right now today. That's based on the 9 state-level drought declarations that have occurred since 1980. So we're calculating that to be a 24% annual chance of a drought declaration any given year. And the most vulnerable critical assets according to our assessment, are related to kind of what you would expect: drinking water supply, power generation, as well as populations that are already experiencing some kind of social vulnerability that happen to be within drought exposure areas. We expect the risk to continue to increase over time, and particularly in not just in eastern and central Washington, but we expect to see drought to impact western Washington more often. This figure depicts the exceptional, extreme, and severe drought from 2021. But it's important to note that in 2021, the entire state did experience abnormally dry conditions for at least part of the year. For extreme weather, this is also a statewide natural hazard, but the most prevalent risk is located in western Washington, with the Puget Sound region specifically the area most at risk. We've had 34 weather-related disasters since 1980, so that equates to a 72% annual chance for an extreme weather-related natural disaster of some kind. And I should mention that extreme weather in our hazard profile includes what you would expect: high winds, extreme rain, but we also do include extreme heat and cold as part of our assessment. Although we are unable to get a disaster declaration based on extreme heat right now. Hopefully that changes in the future. So what's driving the majority of our weather-related disasters in Washington seems to be atmospheric rivers. But I do want to mention that heat is obviously a challenge moving forward, especially after the 2021 event shows just how vulnerable I think we are to heat. We expect the risks to increase, and I think risks will increase particularly in the areas you see in this map. So these counties that are highlighted there represent areas that were in the 75th percentile or above for weather-related disasters since 1980, and there's no indication that that's going to change in the future. So flooding is up next. Flooding is obviously happens around the state, but again, Puget Sound seems to be the area that's most at risk to flooding based on the 30 flood disasters that we've had in the state since 1980, or a 60% annual chance in flood disasters rather. We are a little less confident in our expectation around flood risk. We do expect it to increase, and that's been discussed today. We obviously think floods are going to get worse, but we haven't seen a trend in flood disasters just yet. There's really no discernible trend in floods. We've had an average of about one flood-related natural disaster each year since 1980, and we haven't seen an increase. But we do expect it to worsen. And part of the reason why we're a little less confident in this risk expectation, and why the arrow pointing up is yellow instead of red, has a lot to do with the data available to us to use in our flood risk analyses. We have less data available that we can use for predicting where we think floods might occur. We have FEMA flood maps, for example, which is what you see here in this figure. It shows our 1% and 0.2% annual chance flood zones, but there are large portions of the state where we don't have digitized maps that are available to use. So that makes it a little more difficult in being especially confident in where we think floods are going to be worse, or where we think flood disasters may occur in the future. But we do expect coastal floods as well as riverine flooding to become worse in the future. Landslides are happening, in mountainous and hilly areas statewide, but according to our assessment, the Olympic Peninsula and southwestern Washington seems to be the area most at risk. And again, that's based on where landslides not only occur, but also what happens to be exposed to landslides. So important critical assets that we have to report on in order to meet federal statute that FEMA regulates. So that's important to remember. There's been 22 landslide-related disasters since 1980, or 44% annual chance. We are also a little less confident in where we think landslide risk is expected to increase, largely due to this, precipitation landslide connection is not fully understood, and changes in precipitation are going to cause an unidentified impact on landslide activity. We think areas prone to landslides now are likely to remain prone to landslides. And there's this expectation that the wildfire landslide relationship is expected to increase the frequency and extent of landslides in Washington, or bring landslide risk to areas that are at a lower risk right now. But we don't know exactly where that's going to occur, and we don't have a temporal idea of when we think that might occur either. But we do think that landslide risk will be increasing over time. And then finally, there's wildfire. So as has already been mentioned, wildfire risk is expected to increase statewide, but central Washington, according to our assessment, is the area most at risk today. The figure that you see here is the wildfire hotspot map that we created for updating our hazard mitigation plan. It shows the areas, the most wildfire prone regions of the state based on fires that were reported DNR between 1970 and 2020 that also burned at least 100 acres. So this would be larger wildfires, especially being captured in this map. There's a 70% annual chance of a wildfire declaration, and we include what are called FMAG declarations in that assessment, and that stands for Fire Management Assistance Grants. So these are just-in-time grants that are given to locals that are responsible for suppressing fires that are posing an imminent threat to structures or communities or people. And so the FMAG helps supplement some of these suppression costs. We're seeing extremely large fires occurring in central Washington and eastern Washington. That includes the Cold Springs Pearl Hill complex from 2020 that burned over 400,000 acres. And we see smaller fires in western Washington, although I think Crystal mentioned that there is obviously a potential for very large fires in western Washington, but the frequency of those events is much less. But we also are more developed in western Washington, so a smaller fire can have outsized impacts relative to the fire's size. So a good example of that is the Sumner Grade Fire from 2020, which burned fewer than 1,000 acres in Pierce County, but did cause hundreds of people to evacuate their homes and burned 4 structures. So risk is expected to increase for almost everyone, I think, in Washington. So I'll just end with this slide, which shows disaster declarations by year between 1980 and 2020. You can see over time, there is an obvious increase in the number of disasters declared in the state of Washington. But I do want to mention that it can be a little difficult to fully attribute climate change to that increase shown because disasters are, as I mentioned, also influenced by what's happening, underneath that natural system. So as we see continued population growth in Washington and increasing urbanization happening also in areas that are experiencing more frequent natural hazard events, it's hard to tell what is the primary factor there in that increase. Also, we as a state have improved our ability to get disaster declarations since 1980. We're better at disaster risk assessment. We're better at damage assessments after the fact. And those are important considerations too. And there are more mechanisms to receive a disaster declaration now than there was in 1980. But regardless, one thing we can say is that natural hazards we deal with most often are climate related and occur during conditions that climate change is making more frequent and over a larger portion of our state. So one way to think about it is that harm's way, where harm's way is located, seems to be increasing in geographic scale. And I just want to mention here that all of the disasters declared since 1980, except for the 2001 earthquake and also Mount St. Helens in 1980, were related to some kind of climatic event. So they were wildfires, they were severe weather, they were floods, those kinds of things. And I think that's it for me. So I'll pass it back to Crystal. Thank you.
Great. Thank you, Kevin. I think that was really great summary of the spatial variability of these different risks and a good look at where we're at today. So we do have time left. I'm sure you're all absorbing this information, but we do have about 10 minutes left before we let you all go on time at 2 o'clock. If anybody would like to ask questions, feel free to unmute and you can ask questions of any of our presenters. And while people are thinking about their questions, I'll just go ahead and bring up one more that did come into the chat. There was a question, will more data products like the dynamically downscaled based output for streamflows be available for all Washington regions at high resolution? And Guillaume did answer that in the chat, but just in case others aren't able to see that, Guillaume, do you want to go ahead and say something about that?
Sure. Our dynamically downscaled climate projections are currently available, just not always super easy to access. And so that's actually something we're working on actively. In the chat, I put a link to one aspect of those projections, which is a distillation of what they say about changes in extreme precipitation. But much more could be gleaned from what they say. That's something we're working on. The other thing worth noting with regards to that question is the question was about streamflow projections that would be based on dynamical downscaling. That actually does not exist for the region. So, and that is maybe a topic for further conversation if it's of interest.
Great. Any other questions? One thing I want to add to related to what Guillaume said is as part of the legislation that called for the update to Washington's climate resilience strategy, Climate Impacts Group is also provided some additional funding to make more information and data available to state agencies to support climate resilience efforts. And so that's something we're just starting to work on now. And we're starting by making available some of this information that we've talked about today and other information that we have but haven't made as accessible. We'll also be doing some needs assessment with state agencies to understand what are some of the common priorities and data needs and information needs that we're hearing from multiple state agencies. And these are things that we hope to add to the Climate Impacts Group website over time and build that out so that people can get access to more information. Okay, I see a question here. So are there conversations plans to help store more water in landscapes since it'll not be stored as snow in the future? Yeah, so that's a great question. Today we focus mostly on the drivers and the projections, what we expect from climate change. We didn't get into some of the different solutions and different actions that can be taken, mainly because shortage of time here, but that's really important to understand that there's a lot of different solutions being looked at. Some of the actions that can be taken across state agencies will be covered in the climate resilience strategy. And we also know that multiple different state agencies are putting a lot of work in practice to be able to address some of these impacts. So great. Okay. Well, I think we'll go ahead and wrap up there and let people get off to their next meeting. So we appreciate you taking the time today to listen to this webinar. Thank you again to all our presenters. The emails for the presenters are also provided in the presentation, and I encourage you to reach out with questions, and we will send out an email to the full group when we have both the slides and the recording posted on the Climate Impacts Group website so that you can access that information. So thank you all for participating today. And yeah, we look forward to continued conversations on this topic.